So, in the last lecture, we had become familiar with the generators of the Lorentz group in the vector representation. You see, every group that can be conceived corresponds to a particular symmetry, and when one talks of the generators of the group, what one means is the generation of these symmetry transformations. And furthermore, one can define the elements of the group in terms of these generators. The fundamental relation of importance that follows from the invariance of the Minkowski measure is that the Lorentz transformation matrices acting on the Minkowski metric eta presents us back with the similar form of eta. And when one considers these matrices and their structure close to the identity, that is sort of a linear representation, then one finds the structure of the infinitesimal parameter of the transformation under consideration, and use a trick to define from there the generators. These generators were defined in terms of a matrix capital G that carries the indices of the vector under consideration, the space-time indices, and the other two coordinates, other two indices that coincide with the infinitesimal transformations parameters rho and sigma in our notation. Now, the issue that this full Lorentz transformation matrix have altogether 4 cross 4, 16 components, but what we realized was the capital G's do not have or those do not come in those many numbers, probably because the epsilon mu nu's infinitesimal parameters themselves they do not. How do we actually access this particular any antisymmetric matrix should not have the diagonal members as finite number, their size should be equal to 0. So, what we are left with is, if we have a n by n matrix, then non-zero elements should be n square minus n. But then out of these n square minus n elements, the upper triangular part and the lower triangular part are related to each other by a sign. That is to say, in principle, then we have n square minus n by 2 number of independent elements. The capital G matrices that we are dealing with have two indices in them, and these two indices coincide with the two indices of the infinitesimal transformation parameter epsilon, and was shown in equation number 10. Now, if this G, capital G, would have a non-zero representation when the indices are the same as in the diagonal case, then you can see that since it is contracted with its indices to the same of the infinitesimal parameter, then by the argument of symmetry, the whole thing turns out to be equal to 0. I mean, that is equivalent to saying that the diagonal or elements of G, when G I or something like that, they do not enter into the game. So, the ones those are there to represent the Lorentz algebra are the ones that we have noted earlier prior to arriving at equation number 12. So, we have only 3 spatial rotation generator and 3 boost generators for a system. For physical systems under consideration, one can in principle have varieties of possibilities. If we take a sphere, and if we take, for instance, one cylinder, then a sphere has more symmetry under rotation. That means, you can rotate a sphere in any direction by any angle and would be unable to figure out if the first position was any different from the second, or the second one is any different from the first. On the other hand, if we take a cylinder for that matter, this freedom is sacrificed, except for rotation about one axis. So, you see that one of the symmetry generators does not actually generate the symmetry that it should have otherwise done. So, those are the generators corresponding to the broken symmetry, and this breaking can happen in rotation, in the operation of rotation, or whatever the case may be, the representation of a group, Lorentz group, if it is defined by a symbol of capital D, then by construction D of argument A, small a, and D of argument B, small b, put in the order D of A times D of B should give me D of argument A B. To make sense of this definition, we also have to put that value that D of 1 should correspond to. So, in that situation, when D of 1 is equal to what? We can figure it out from the definition that is written on the top mathematical equation of this slide, that D of A should give me back D of A. And if from this relation I have to get this result consistently, then we should better have D of 1 equal to 1, because if we have a look at this expression, if we set B to be equal to 1, what we realize is D of A equal to D of A, and that is a trivial, but a important relation at this stage. So, that fixes the fact that D of 1 must be equal to 1. The elements that we have defined here in terms of small a or small b as the arguments of capital B are actually the Lorentz transformation matrices lambdas that we have defined earlier. Now, if we again go back to the first equation, consider my small a to be a Lorentz transformation matrix and my small to b to be inverse of the Lorentz transformation matrix, then D of Lorentz transformation matrix lambda times D of Lorentz transformation matrices inverse, that is lambda inverse, should give me D of lambda times lambda inverse as an argument, and by the condition if lambdas are not singular and lambdas are invertible, then this gives me to my right side D of just 1, which is equal to 1. So, my representation for a particular transformation lambda is equal to the inverse of the transformation with arguments the Lorentz transformation matrices inverse. And for an infinitesimal Lorentz transformation, what we said a while ago is true for any finite Lorentz transformation. but for infinitesimal Lorentz transformation, if we want to find out the representation of the group, then it is given by identity plus half of epsilon mu nu times g of mu nu in the vector representation. In principle, as there are objects that exist in pages of mathematics and as puzzles of nature that can be termed as the scalars, the spinors, the vectors, the tensors, the mixed tensors, etc. These representations can also vary from one to the other, but we will stick to this particular representation because we are interested to investigate the propagation of vector type of disturbances or vectorial disturbances, not anything else at the moment. So, our G's now I have decomposed them into two kinds of stuff. One, the spatial part represented collectively by capital M, where G of 2 3 corresponds to M 1, G of 3 1 corresponds to M 2, and so on and so forth, and G of 1 4, G of 2 4, G of 3 4 corresponds to the boost generators N, and their commutation relations among their ilk and outside are noted in equation 16. This particular piece of equation that is given by 16 tells you that the algebra is actually not closing into itself. So, there may be a representation if we combine these pieces of M and N together such that the commutation relations among them of the same kind should produce an element that belongs to the same collection, and if you take commutation relations belonging to two groups, you will get a trivial result which is 0. That means, whichever order you execute the process does not going to dictate or does not going to change your observation, and we will just leave this particular topic out of our discussion for the time being and move on to find out the elements of the group in terms of this infinitesimal Lorentz transformation. So, to do that we can define these parameters, that is Lorentz transformation parameters, those are infinitesimal, by infinitesimal quantities theta prime and chi prime, and we further can say that if we take a ratio of theta prime by a natural number n to be equal to theta and the ratio of chi prime by a natural number n equal to chi, such that in the limit of very large n these ratios reproduce a quantity that can be called theta and chi, then this product of epsilon times g alpha beta that actually comes as capital M times theta prime plus capital N times chi prime can further be written as capital M into theta plus capital N into chi divided by n overall, when n is a very large number. So, with this in the background, we can now quantify the statement of infinitesimal Lorentz transformation of a quantity that is given by capital A in bold prime should be equal to the bold A itself plus a little variation that comes from two sectors. One sector is from rotation and the other sector is boost. So, what we have is capital M into theta prime into A plus capital N into chi prime into A. The same thing I think is displayed here right before us on the screen. So, what we are going to see now is this is a character or this is the expression for the infinitesimal Lorentz transformation. But if we want to build something which is finite, we should be able to harp on the results of infinitesimal Lorentz transformation. And this turns out to be possible if we recall the relation that is given by equation 20 that gives us 1 plus x over n to the power small n in the limit n goes to infinity exponentiates the x and it leaves us with e to the power x. So, we can keep applying this infinitesimal transformation again and again and again and again and again to generate what is given by the equation number 21st, saying that A prime can now be related to A by the exponentiation of the rotation matrices and the boost matrices or boost generators, not the matrices. They are indeed in general, but boost generators and the boost rotation generators M and N, capital M and capital N. The structure of these matrices capital M and capital N can in turn be related to the matrix G's, G either spatial indices or the temporal indices. And we recall that if we take the product of these G's with themselves, that is G 23 square, G 23 cube, G 23 power 4 etc., then it can be verified that they produce either the G's themselves or unity matrix identity. So, if we have something like what is written in equation 22nd, then we can write the same thing in terms of cosine and sine and expand these arguments inside cosine or inside sine. Then you would arrive at a matrix which is typically a rotation matrix, where the rotation is confined to the or on the x y plane. There is a factor of I that should have been there in equation 22nd before the sign, but we will assume that it is there, and then we will move on with the rest of the derivation and we will correct it in future. So, equation 23 now gives us essentially the rotation, the result of, or result or is the rotation matrix about the z axis, and when the rotation is taking place on the x y plane. For most of the situations that we encounter, when a beam of light is coming towards us, if we fix the direction of propagation of the beam of light to be the z direction, and the plane on which the vibration of the electromagnetic disturbances takes place to be x y plane, then this particular matrix actually is suitable to describe any rotation of either the observer or the source to find their possible implications. So, what happens when a rotation like that takes place? It is simply for a 4-dimensional system, the 1 and 2 elements are mixed among each other, leaving 0th and the 3rd variables the same. So, you can write q prime 0 to q prime 1, q prime 2, q prime 3 equal to the rotation matrix times the unprimed components of the q vector. And what is so great about it? The greatness lies in the fact that the inner product in this case remains the same, but the direct product need not be the same, they are different. And this has a profound consequence on the polarimetric variables that we often use to describe the polarization properties of a beam of light. Thank you.